So the last thing that I want to talk about in our unit on bonding is just a comparison of the different bond types and the properties that spring up from those different bond types. Go ahead and, you want to pause here and try to replicate sort of the table that you see there. Leave yourself some space for a few words in each box. Okay, so let's start with an example of each type. So classic example of an ionic compound probably be sodium chloride, NaCl. Whereas covalent example, maybe we'll go with carbon dioxide, CO2. The metallic, we could go with aluminum, iron, a bunch of different metals. Don't forget though too that alloys would be metallically bonded as well. So things like brass, bronze, stainless steel, those are alloys, but those are metallically bonded. Now, an important distinction to make with the formula is for an ionic compound, the formula tells us a reduced ratio of ions. Okay, but when we look at a covalent compound, it's a little bit different. It's not reduced necessarily. So it's the number of atoms in the molecule. And it's not necessarily reduced. So you could have something like C2H4 or, P2O6, anything that, any combination that actually shows up in a molecule would be written in the formula. Whereas with an ionic compound, it's just a reduced ratio, because with an ionic compound, what you have is just, crystal. So that crystal can be just a repetition of positive and negative ions over and over and over again, usually trillions and trillions of times. So when we write the formula, all we're doing is saying that, the ratio is 1-to-1 or the ratio is 1-to-2 or whatever the case may be. But with a covalent compound, each molecule is discrete. It is its own thing. So you don't find NaCl formula units by themselves a lot, but CO2, carbon dioxide molecules, do float around independent of each other as a discrete unit. When it comes to formulas for metallic bonds or for metallic compounds or elements, it doesn't really apply. You don't really write a formula for an ionic compound. You can have like recipes or mixtures of different alloys of different compositions, but we're not really going to get into that. The Lewis structure. So for an ionic compound, this is something you already know, but just to review it, your Lewis structures for ions are just going to be the ions with dots, and we used X's to indicate gained electrons. And then the negative ion, the anion, has its little bracket, and they both have a charge given. Whereas the Lewis structure for a molecule, we've done a bunch of times, is going to be a little bit more like this, with your shared electrons shown as the little lines. And then again, Lewis structures for for metallic bonds, not really necessary. All right, let's compare some properties here. Melting points for ionic compounds, extremely high. And you can say that it is related to high lattice energy, or LE. We talked about that already. All ionic compounds have high lattice energies. Of course, they vary depending on charge and sizes of ions, which we've talked about before. But the crystal lattice is very difficult to break down with heat. So melting points of all ionic compounds are going to be really high. And then when it comes to covalent compounds, they tend to be a bit lower. So we would say most are low. Like CO2, of course, is a gas at room temperature. And there are some higher ones. I mean, you have some exceptions like, graphite and diamond and things like that with extremely high melting and boiling points. But for the most part, your covalent compounds, think about things like sugar, relatively low melting point, Gases like methane, CH4, NH3, which is ammonia, those are gases at room temperature, so low boiling and melting points. And then things like plastics that are solids at room temperature still have pretty low melting points. Metals, of course, are going to be high, most of them. Oops, let's stick with my blue color. So most are high. There are some exceptions. Gallium is pretty close to body temperature. You can melt a chunk of gallium just by holding it in your hand. Mercury is, of course, a liquid at room temperature, so it's really low, but most of them are pretty high. Malleability. So for the ionic compounds, they are brittle, not malleable. And we talked about this in class when we talked about metallic bonding. The ions of like charge line up and they crack, they break apart. The covalent compounds tend to be malleable if we're talking about things like plastics. I would say most are malleable. There are some exceptions, again, like graphite and diamond in the case of carbon. Also, solid sulfur can be a bit brittle as well. But I would say most of them are malleable. Again, talking about things like plastic, those tend to be bendable without breaking. And then metals do tend to be malleable, although that does vary. We have some metals that will break, not really shatter like ionic compounds, but will tend to break with enough force added instead of bending. Okay, solubility in water. I'm going to go ahead and say right away that doesn't really apply to metals. Metals don't dissolve in water. Ionic compounds, most are soluble. And that's because those positive and negative ions can get surrounded by water molecules that are polar and pulled apart. On the other hand, covalent compounds, we would say only polar molecules are soluble. And again, that's because like dissolves like. So nonpolar molecules like oil aren't going to dissolve in water. And finally, electrical conductivity. Ionic compounds, when you dissolve them, will conduct electricity. So I'm going to say when dissolved. Whereas covalent, not conductive when dissolved, also not conductive when not dissolved. So like if you have solid sulfur or something like that, not going to be superconductive. One exception, again, going back to graphite, it does have a free electron that can move around and conduct some electricity to some extent. But for the most part, your covalent compounds are not conductive. And they're definitely not conductive in water when you dissolve them. So if you had a sample of a white solid and you wanted to know whether it was salt or sugar, you could test its conductivity. Does it conduct electricity when dissolved in water? If it doesn't, then you've got a covalent compound. If it does, it's probably ionic. And of course, metals are, I'm just going to say yes, conductive in solid form. So a couple important properties just to kind of tie everything together, and also a good way to identify something. Again, if you have two crystalline solids, could be ionic, could be covalent. You can look at their melting points, their conductivity in water, their solubility in water. All of those things are going to be helpful in terms of determining which one it is.